All right, mic check, mic check. Sorry for the delay. I'm just giving everyone another minute or so. All right, mic check, mic check. Sorry for the delay. I'm just giving everyone another minute or so. All right, mic check, mic check. There we go. All right, mic check again. All right, welcome everyone online. I apologize. I tried to get the YouTube stream early and it was being finicky with me, and it always takes about 10 minutes to warm up and show. And I thought I started early enough, but obviously not. All right, so let's actually get started for a lecture, and hopefully things work. And again, I apologize. Thank you for verifying in the chat that you can hear me as well. Appreciate that. And so I'm watching the chat live, so if you have questions or anything, just keep them coming and I can watch. All right, so welcome to CHEM 104. So as you guys have probably figured out by now, this is a hybrid class, so it's being offered in person. So welcome to all y'all in person. Then we're streaming it live, and then why I went through the trouble of putting it on YouTube is so, of course, the YouTube video will be available immediately after, and I'm bypassing the Zoom mess of trying to upload it later, which always causes delays for students. Oh, this was awkward. Sorry, I lost my mouse, apparently. Did my computer freeze? Oh, no. Sorry, this is technical difficulties of class, apparently. There we go. All right, my mouse, sorry, stopped working. All right, I apologize. So let's continue. Now that my mouse is happy. Are you kidding me? Whoa. Seriously? Okay. All right, is the stream still going? I just don't know why everything is frozen. My Wacom.
It does show you as frozen.
Okay.
But your voice isn't, you can hear everything.
Is it still going?
Oh, wait, no, not now.
All right, I have no idea what's up. I don't think this computer can handle it or something.
Maybe it's the Wi-Fi?
It shouldn't be the Wi-Fi.
The video seems fine, it's just your webcam that's frozen.
Yeah, for some reason, like so I have this little hub here, and nothing that's plugged in there is working, which is my Wacom.
Somehow turned off?
It sits on. So I have this little hub here. I can.
Oh, there's a delay. That's fine.
Yeah, there's obviously a delay for stream, but I just can't figure out why now my USB hub isn't working. All right. If you're online, can you still see? All right, I lost my mouse, so no more mouse. All right, are we back? Test, hi, I am so sorry. So now we've wasted 20 minutes of class thanks to technical difficulties. So I apologize. You'll soon learn that apparently my classes are all cursed, and what will go wrong does go wrong in terms of technology. And I have zero support. All right, so what I want to do, though, is kind of go over how things are run and what to do. And again, I don't have a mouse, so this is really painful now. So everything you need is on your Gradescope here, your Blackboard. So we have week 1, and then, so a lot of people have complained that all the dates are wrong. I apologize, I'm trying very hard, but obviously every file is named with a specific date, so I have to rename every file, which is beyond tedious. So please refer to the syllabus. So the syllabus doesn't work. All right, so the syllabus is correct. And I apologize because I don't like Concourse at all. It's horrible. But this is accurate. So you want to follow this. This is where all your due dates are. Everything is laid out here. And then I have it set up so week 1, I try to lay out what assignments are due. And if you look under the recitation section, you'll find that there are answers there to the homework already. But the homework's there as a practice and a guide. And hopefully we still have the online students. Oh, crap. Because I lost them. I forgot that they can barely hear me because I don't have a camera now, or a microphone. What am I doing? Oh, you can hear me? Can you hear me or no? I can't tell because my webcam is not lit up, even though it's supposed to be.
Yeah, it's like a really long delay now, like 25 seconds.
Okay. Well, at least it's working. All right. Okay, good. Thanks, chat. Again, I apologize. I have no idea what's going on. This is probably the worst class in a while in terms of technical difficulties. All right, so for turning in labs, because again, there's 50-something of you in total and one of me. So to make it easier for myself and for grading, and so you get detailed input, go to gradescope.com, and then it should be, the entry code should be in the syllabus, so that's YV3ZVW up here, and so apparently no one's joined this course yet. So please do this ASAP, so that'll be useful when we start doing labs next week. And then you've probably discovered that I have all the old lecture materials there, so you can look there for past lectures. And then, of course, lab materials are all here. And then if you're joining us online, then you'll watch the videos to complete the labs. And then, of course, if you're in person, you'll do the labs in person. And if you would like to join us in person, then just let me know, and usually there is room. So hopefully the stream's looking good. Don't know why my video is still frozen. All right. So are there any questions or comments? Yeah.
So we'll be able to rewatch the lecture since it's posted on YouTube?
Ideally, yes. That is the entire plan.
Okay, I think this has been a pretty informative 20 minutes of class if we start now.
Okay. Again, I apologize for everything.
Not your fault. The tech's fault.
All right, so what is chemistry? So I'm pretty biased. I like chemistry. But chemistry is what I think one of the central sciences. And why I say it's central is because it's related to so many things. So what are your majors? So if you're in the chat too, I want to hear, like, what are your majors? What are you going to study?
Medical malpractice attorney.
Nice. So that's a good one. So medical malpractice, right? So then you have fundamentals with chemistry. You got to understand how things work on a molecular level, that we can develop a lot of materials too based off of chemical properties. What else do we have in here? So nursing, I see nursing in the chat too. So nursing, you've got to know your units. Units are important so you can understand how much to dose somebody, do conversions, be able to look to, like, does that look like a mg? Does that look like a microliter? And I see elementary education, so of course chemistry gives you good foundations for just logic too. What else do we have? So of course medicine. We've said a lot of medicine, but we could also go into drug development. Drug development's really huge. Let's put big dollar signs around medicine. So pharma. So of course biology as well. It's tied to understanding kind of the fundamentals, especially your acid-base chemistry that dictates a lot of how the body operates. So food science too is pretty related, so you could go to like the chemistry of foods and also how your body processes food. I see pre-professional medical technology in the chat. So again, that's technology that could be materials, developing new materials. Oh, don't forget ag. So ag's a big one. So right now, with the conflict in Ukraine, so about 80% of the world's ammonia is made in Russia right now. So ammonia is made through the Haber-Bosch process, which is extremely energy intensive. I think it takes 1% of the world's energy. And so if we could figure out how to do nitrogen fixation at ambient temperatures, that would save us a lot of money. Otherwise, you know, people are worried about food shortages if we have a disruption in ammonia, which is of course essential in fertilizer. And then chemistry is also related to geology, of course, and no one doing geology or anything in here. I always think geology is more like applied chemistry. See how things, of course, yeah, how they form in nature, a lot of oxide compounds, silicon oxide. And then, of course, energy. If you care about energy, you probably want to look into nuclear chemistry. So that's, of course, very energy dense. And that's also related to physics and math, of course. I would say that these all help us understand chemistry. And then computer science can also be related, not only through the materials, but also computational chemistry is really important to help us understand. And then nanotechnology, this could apply to not only materials, but also drug development, cancer treatments. So all sorts of things. So chemistry is related to everything. And so chemistry we can also define as the study of matter. So what is matter? So matter is anything that has mass and takes up space. So of course this desk is matter. My camera's probably not firing, so that probably doesn't help the online students. And then matter can of course change from one form to the other in a chemical reaction. So we'll learn about chemical changes. And so we're not destroying any atoms, we'll just learn that they rearrange to make different materials. So rearrangement of atoms. Oh, just trying to use my mouse, it doesn't work. And so one example of this is if you were to just take propane. So of course you can buy propane at a gas station. And then if you put it in your grill, right, what you're doing is burning it. So of course that propane is being converted to carbon dioxide and water, and is also giving us heat. And then we'll look at physical changes. So physical changes, matter does not lose its identity, so the atoms all stay the same, but we just instead do a state change. And so we'll look at what that means. And of course, ice is one of the substances that we can see at all different states of matter regularly. So you probably have some ice in your refrigerator at home, and then you could pull it out, right, watch it melt if you're really bored. And then, of course, you can also boil it, and you want some hot tea, and then you can watch that steam rise. So, of course, that would be an example of physical change. And then, again, feel free to stop me if you have questions, and if you're watching, again, just pop your question in, and I'll address it. Yeah.
So, plasma, is that just like the electrons are free flowing essentially, or how does that work? Are we not really going to cover that currently?
We won't really cover plasma because plasma is only really found in extreme high temperatures, and it's more like this gaseous special state. But
Okay, so it's closer to like, I don't know much about
so it'd be found on the sun. So like the sun, right? It's really high energy, and everything's obviously at a ridiculously high temperature, and so that's the state of, fusion. But we won't focus on that since it's not readily found. So matter can be classified according to its states, and so we can identify its states as solid, liquid, or gas. Again, we don't care about plasma since when we do reactions in general, right, we're not going to add a plasma compound or anything, so instead it should be in this solid, liquid, or gas. And so now how do we tell what's what? And so let's look at this at kind of a molecular level. So if we have a solid matter, so notice the atoms are packed really close together, so they should be packed so tightly that they're not going to move, right? So they're just packed solid in place. You still have, of course, some electronic movement, still have vibration, right? So we don't have no movement, but the atoms are not going to slide past one another. They're just going to stay in their solid form.
Don't the atoms also have less energy?
Yeah, so they would have less energy too. Good. So let's just add that. So less energy. And then, so if we put more energy into them, we're going to break what are called intermolecular. And this is kind of for later. But just putting that term in your head, so we're looking at these intermolecular forces, so between molecules. And so we add some energy to them, so now we make it so where if they're in the liquid state, so now the atoms can kind of slide past one another, they have a little bit more energy, and so now they're kind of moving around. And what about the volume of liquids, though? So is the volume consistent for a liquid? So I see a thumbs up.
Oh, volume, yeah, volume is consistent.
So exactly. So volume, constant, but it can change shape. So we know that, right? You can take your water from your tap or wherever, pour it into whatever shaped glass, and it will, of course, fill that space. And then so in gaseous, we're to take this material, now it's filling up this whole Erlenmeyer. And so now we've added even more energy, so kind of thinking about energy. And so now the particles are further apart, so now they're more widely spaced. We generally start to ignore the intermolecular forces and interactions, but instead now they're just spaced apart atoms or molecules floating around. And so let's look at all the definitions. So for a solid, like we said, the atoms or molecules packed closely in a fixed location. And so again, they do have vibrational movement, but they cannot actually slide past one another. And so because of that, we always say that solids have a fixed volume and a rigid shape. And so ice, aluminum, diamond, those are all just examples of solids. So in a liquid, so like we were looking at, so now they pack closely, but they are now free to move relative to each other. So again, they can slide past. And so like you were saying, we know that liquids have a fixed volume, but not a fixed shape. So they can take the form of any container based upon their ability to flow. So of course we talked a lot about water, where you can have alcohol, or gasoline, many other liquid substances. And then for gaseous matter, so now they have a lot of space between them. And I'll just add 10 to ignore intermolecular interactions. So again, now they're spaced out so far apart that they don't even care about their neighbors. They're just moving around randomly. So they're moving around. And of course, we could also take this gas and compress it. And so this gas, this means that gases are compressible. So maybe you've seen like those giant liquid nitrogen containers that they use to fill up your tires with. Yeah, I see some nods. So right, you have liquid nitrogen, starts off, it's a liquid, and they keep it under pressure. And then of course you open up the nozzle to hook it up to your tires, and out comes, the gas as it comes spewing out into the atmosphere. And of course solids, right, by contrast, are not compressible, so you can't, right, take a rock and try to squish it down to occupy less space. So now let's look at how to classify matter. And so we have this little flow chart. So we'll start with matter. Then we'll ask ourselves, so is it one type of particle? So does it have kind of one substance in there? Or is it different substances? And so if it's different substances, that would be a mixture. And so a homogeneous mixture is uniform throughout. So I always like to say, kind of the first bite same as last. And so I always think of, right, you got Gatorade, so you buy your Gatorade, so you take your first sip, it's the exact same homogeneous concentration throughout of whatever is in Gatorade, so a mixture of water, sugar, electrolytes, all those good things, and it doesn't matter where you sample from, it will always be the same. And so that's compared to a heterogeneous mixture. And so a heterogeneous would not be uniform. And so what they're showing is sand. So you can, if you take some beachy sand, you'll have like the top of your cup will probably be clear. The bottom of it will be really sandy. Can you think of some other heterogeneous mixtures? Yeah.
Shoot, I had one, and then as soon as I raised my hand, it popped out of my head. I apologize.
No worries. Other ones?
The ocean is one.
Yeah, I think dirt's a big one.
So the ocean, it kind of depends like where you sample from. I guess if you're taking the whole ocean.
I'm saying the ocean as a whole, technically, as if you consider all the different fish or different compounds in it.
Yeah,
Or is that too broad?
that might just be a little broad. So let's think about, so you mentioned dirt. So dirt, that could also, if you
Pond water, maybe?
so pond water is a better heterogeneous. So pond water, right, because you could have some parts that are clear, some parts with little fish in it or whatever. Yeah.
Good soup.
Yeah, soup would be a good heterogeneous. So you got chunks in it. So dirt would also be good, especially if it's, again, not uniform. So if you have sand, you could kind of argue, you know, that it might be more homogeneous depending if there's like giant rocks in it or not. So other heterogeneous things that we can think of. Burning examples.
A milkshake.
A milkshake. I'll add like a Oreo milkshake. So it's clear that there's chunks in it. Since you could argue that like a really well-made milkshake could be homogeneous if it's just vanilla. So I see grass. Grass is just, I guess we could put that in for heterogeneous.
Bad coffee.
What kind of coffee?
I said bad coffee.
Bad or bag?
Bad. Where it's
Bad.
like, it hasn't been done all the way. You maybe didn't include the filter, so there's like a bunch of particulates floating in it. It's all grainy.
So I'll put unfiltered coffee. All right. Yes, and then so in the chat, so somebody asked, so homogeneous would be broth. Exactly, so broth, that'd be a homogeneous mixture, so again, all clear throughout. And then you put your broth to make your chicken soup or veggie soup, whatever, and so that would be heterogeneous. All right, excellent examples and thinking. And so for pure substances, so now pure substances, you're basically trying to distinguish between is it an atom or is it a compound? And of course, atom and element can be used kind of interchangeably. And I need to put a periodic table in this room. And so you have to ask, is it a pure substance? So is it, right, a molecule? Does it have a defined chemical formula? Yeah.
So for element, it's just the number of protons that matter. It doesn't matter isotopes or ionics at all.
Right, so you just care about, like, is it the same element? So, because that'd be asking, like, too much to distinguish between, like, the carbon isotopes. But we could say, right, so carbon, that's an element, and so carbon's just a bunch of black powder. And so looking at that black powder, we don't need to distinguish between the isotopes or anything. It's just, it is carbon, that's an element, so that's a substance.
It's got six protons, only use protons in all of it, then be good.
Exactly. And so that's how, and we'll get to the whole proton thing, so don't worry. We'll get there so everyone's on the same page. And so compounds are anything that have, of course, multiple atoms in them, but they are a defined chemical formula. And so that is really the distinction. So defined chemical formula. And so that can be like aspirin, right? But then sometimes if you take a pill of aspirin, it could be aspirin plus like some other medication or like
some filler or something.
Right.
Like some dyes.
Yes.
Some like flavor compounds or whatever, etc.
Exactly. So you kind of have to distinguish, like a pill could be with gelatin and something or fillers, and then versus the actual kind of compound itself. And then any other examples of elements and compounds, we'll kind of look at more in detail.
So for the compound, the chirality wouldn't make a difference though, right?
Yeah, that would be something else, like distinguishing R and S.
Chirality is like the direction of the molecule, right? Like if it's the left side or the right side, or am I thinking of something else?
No, that's chirality. So it means like handedness.
Yeah, the whole fun thing of left-handed sugar tasting the exact same, but being pretty much useless to the body. You could eat it and you would die of starvation.
Oh, and then someone in the chat said gold. And so exactly, an element does not separate into another substance. And then, let's see, did I put a periodic? Oh, I forgot a periodic table. Sorry, let me just paste one in from somewhere. This is not the one I like. And so just to clarify, since we don't have a periodic table in this room, and we're also streaming, so anything on the periodic table is going to be an element, right? It can't be broken down into another substance. We're ignoring the fact that you can change things through nuclear chemistry. That's kind of set aside for its own discussion. But so you find it on the periodic table, that means it's an element, and correct, it cannot be broken down any further. Great questions from the chat. All right, so kind of a recap here. So again, a pure substance is only made up of one component, and a mixture is two components. So anytime you have two or more either elements or compounds, now you have a mixture. So another common mixture, before I forget, is of course the air we breathe. So obviously there's nitrogen and oxygen in there, and argon, and so that's a mixture. And then so question from the chat, is an element a defined molecule? So element is just on the periodic table. And then that means that molecules, right, are made up of different elements. So I guess we could say that a molecule has 2+ different elements. So it has to have 2 different elements. And so we'll go to that in a second. So looking at mixtures, so again, we went over heterogeneous versus homogeneous, and y'all came up with a bunch of great examples for heterogeneous, so salt and sand mixtures, versus homogeneous. So again, we said kind of this first bite, same as the last, kind of like sweet tea if you make it properly, right? It'll have the uniform amount of sugar throughout. So again, uniform composition. Oh, And then, so let's go back to elements versus compounds for a second. And so I wanted to emphasize something. So we have some elements, they may fool you. So we have what are called the diatomics. So the diatomic elements are basically elements that are not found by themselves, and so they're always going to be paired. And so you know them, I'll highlight them, and then I'll write them out. So hydrogen, and then the rest make this like little 7 over here. So starting from nitrogen, then going to oxygen, fluorine, chlorine, bromine, and iodine. So all these are diatomics, so I'll write them. So hydrogen, nitrogen, fluorine, oxygen, chlorine, bromine, and iodine. So there are 7 diatomics. And so even though, right, they have a little 2 here, they're still elements. So this is their elemental form. So still an element. And then we also have other substances that appear as allotropes. And so some of those are going to be, actually let me restart this. So carbon, for example, has a different allotropes. And so all this means is that there are different forms of it. Let me pull up a picture, just so we can get a better idea of what I'm talking about. Yeah, so they have different, they differ in their structures, whoops. And so so if you can notice that, it's got like the tetrahedral geometry. So these are all, again, just pure carbons. So again, it's an element. But in A here, it's in this, again, tetrahedral pattern. So this would be diamond. This B here, so notice how they're in sheets. And so since they're in these sheets, that's going to be graphene. So when you write, that's what's shearing off is these little sheets of graphene. And then let's see, I'm not quite sure what everybody else is. So this H here, that's a carbon nanotube. And then I believe D is a buckyball. So that's C60. So again, they're just different forms of carbon. And again, still an element, even though they have formulas now of C60 for the buckyball. And then we'll add in there diamond, graphene. Other elements with allotropes that may confuse you. So sulfur is the next one. Oh, come on. So sulfur is not just a lone little sulfur. So if you have elemental sulfur, sulfur is actually occurs in this little ring here. So the formula is S8, but again, that's still considered an element. So S8, still an element. And then, so kind of last big example is phosphorus. So phosphorus has a few allotropes, so white, red, yellow, violet. And so again, they just have different structures that give them different properties. So of course, some of these are used as weapons in war. So I'll just add, right, P4, so phosphorus. So again, has different allotropes. Right, so hopefully that clarifies kind of elements versus compounds. So then compounds, right, have different distinct atoms instead of just multiples of the same one. And then, so kind of the next concept is, well, how do we separate it? And so this is just a simple distillation apparatus. And so I like to joke, you know, anyone can mix stuff together. Or actually, I shouldn't say that I said this. So I had an old boss that said, my 3-year-old can mix things together, but being able to separate them out, you know, that is more difficult. And so most of chemistry is just trying to purify and separate things out. So this is just an example of a simple distillation apparatus. So you could have, let's say you had salt water, if you were stranded on a desert island and then wanted to get some pure water, so you can add a heat source of some kind. Probably wouldn't want to use an open flame, not very safe. But then you heat it up, it goes up here, recondenses since you have this water condenser here, and then your whatever solvent you're purifying comes down and distills into your receiving flask. That's just the basic, how to distill, how to separate. So now let's shift to units and unit conversion. And so let's first look at, so, you know, why do units matter? And I know a lot of you said that you were going into the nursing field, so again, units really matter, being able to understand the difference. And so here's a little story. So we have a Boeing Delta aircraft was launched, and so the software that they used to calculate the force on the thrusters was in pounds. And then another piece of code assumed that it was newtons per square. And then the other engineers, so the Lockheed Martin people, expressed force in pounds. And they did not do the conversion to metric units. So NASA was working with the wrong numbers, didn't have them. And so what happened, right, they launched it into space, something wasn't right because the units were wrong. And so when the spacecraft entered the atmosphere of Mars, it entered too close, probably too fast, and so it ended up burning up and breaking into a bunch of pieces. So I don't know how many millions or dollars were lost there.
So it still made it to Mars, just not in one piece.
Exactly.
That's a celebration, I guess.
Yeah, when you invest a lot of time and the error was in units, right, that's not good. So that's why units matter. And then, so our other issue is, right, science kind of works with everything. We work from the really small to the really big, and so we have to use kind of metric units. Let's just play a game. So what do you think a human hair, what do you think the width is? Roughly, order of magnitude, or
5 nanometers?
so that's pretty good. It's not quite as small as nanometers.
Sorry, micrometers. No?
Yeah, micrometers.
Sorry, micro.
So we'll say about 5 or so. I think it depends, maybe 5 to 40, but on the order of micrometers. What about atoms?
I want to say like picometers or something of the sort, or is that wrong?
No, so picometers would be 1 unit, so that's 1 times 10 to the negative 9th we'll learn. But,
That's not nearly small enough.
well, chemists also use angstroms, and that's 1 times 10 to the negative 10. This is just not like a normal unit. But, again, good job with the order of magnitude. What about an elephant? How much does it weigh? Any guesses?
Well, it would be in kilograms specifically, is what it would be weighed in. I'd say around 2 to 3,000.
Yeah, you got your guesses correct. So yeah, again, on the order of kilograms, I see 2 tons in the chat, so tons is another unit of measurement. Again, we don't typically use it,
Metric or imperial?
we're mainly discussing metric, but
I metric
Oh, I'm not sure.
Sorry for taking up. Someone else can answer this next one.
And then what about distance to the nearest star?
It'd be in like light years away.
So light years. Any guess? Anybody know?
I believe, let's see, Alpha Centauri. I want to say, let's see, what do you think? I want to say like 9, but it could be closer to 70. I'm trying to remember. Sorry.
So 4.35 is what.
Okay, right.
And then, so I'll give it to you in kilometers. So that would be 4.11 times 10 to the 13 kilometers, which is, of course, kind of crazy to think about. And I see in the chat too, so light years. So excellent, right? So we've kind of seen the point that we're all over the place in terms of our units, right? We're looking at atoms, which we can't even see. Now we're trying to measure distance to the stars, which, you know, I can't even think of what 10 to the power of 13 kilometers is. And then light years.
About the time it takes light to travel in 4.35 years.
Yeah, well, I can't imagine that. That's pretty crazy. So let's look at this, how the metric unit is set up. And so we have what are called our base units. And so each type of measurement has a base unit. So we have, class ends at 6:30, or I guess 6:20, right? Okay, just making sure. So moles, so this is a special quantity for chemistry, but we can have like micromoles, millimoles, length, so your standard length is in meters. Yeah.
Wait, I thought you, in like chemistry and stuff, we used Kelvin.
So Kelvin, that would be for temperature, and so we could put Kelvin under there.
Because it's basically just Celsius, but instead of starting at the freezing point of water, it starts at, well, the theoretical absolute 0.
Exactly.
Easier.
Yeah, so Kelvin comes up more with like thermodynamics and and like gas laws. And then we just put Celsius since that's generally common. And then so volume, your base unit is liters, time is seconds, and then information, bytes. And so the metric system is based on multiples of 10, which makes it a lot easier. And so multiples of 10 are created by adding a prefix to each base unit. So for example, we can use centi to show that it's 1/100th of a meter. And then, so let's look at this metric prefix. And then I'm also going to hand out, because we're going to go to a next slide in a second. So if you're in class, I just have this extra conversion chart. And so kind of the trick is to understand how to read this thing. And I don't like this one. I think this one's kind of more confusing because this says quantity in 1 base unit. So this means that compared to our base unit, and see, to me this doesn't really make sense, but it's saying that it's 10 to the power of -3 times your base unit. But, so what I handed out was this. I think this is easier to understand, but we'll go through it. So this is your multiplier, and so this is by your base unit. And then the conversion factor, this is just going to be our little fraction that we write, but you'll see what I mean in a second. So we want to set up our conversion factors, and then there's kind of 2 conversion factors. And so what I mean by that is if we look at milli over here, so milli's done for us. And so milli, again, this is times the base unit. So it's 1 times 10 to the negative 3 times our base unit. And so that means that we could say we have 1 times 10. So the chart should just be in the next page, and I posted the notes so you can get the OneNote notes and also the PDF form so you can get this chart. But we can say 1 times 10 to the negative 3 meters, if we're looking at just our base unit of meters, equals 1 millimeter, because again, that's times your base unit. But for me personally, so we could technically write 4 conversion factors. So we could write 1 times 10 to the negative 3rd millimeters, or excuse me, meters, I wrote that wrong. Meters equals 1 millimeter. But for me personally, I don't like thinking in negative exponents. It's easier if you keep everything in positive exponents. So you can multiply everything 1 times 10 to the 3rd. And so it gives us this conversion factor, which is just 1 meter is equal to 1,000 millimeters. So that's what's written here. So they just wrote their conversion factors using positive exponents. And then if you can write it this way, right, 1 meter over 1,000 millimeters, you can also write it kind of the opposite way. So 1,000 millimeters over 1 meter. And so you need the two depending on which way you're going. So if you're trying to end up with final units of millimeters, you're going to want to use this one if you're going from meters to millimeters. Otherwise, you pick the second one. And again, we'll go over some math together so everyone's not confused. But I would go and fill in this chart. And so let's do some together. So we could say 1 times 10 to the 9th nanometers gives you 1 meter, or 1 base unit. Because again, this is times your base unit. And so you can think, right, they're really, really tiny. So you're going to need a lot of them to get back to your base unit. And of course, we can write it the other way too. So 1 meter is equal to 1 times 10 to the 9th nanometers. And then, so let's fill this in for pico. So the 9 just came from this nano here, this negative 9. And then, so again, it's times your base unit. So if you're confused, right, you can say, well, I know 1 times 10 to the negative 9 meters is equal to 1 nanometer, because that's what this is saying. But again, we don't like using negative exponents. You can, I want to make that clear, right? You can use them in your dimensional analysis. But it's just people tend to screw things up when you're actually working it out and you have a negative exponent, something goes wrong. So that's why I encourage you to use these kind of positive ones. And then, again, if you set this up, so we have, if you're not quite sure, just reading off this chart, okay, so I know that one of these is equal to 1 nanometer, but now I want positive exponents, so you can do a little math trick of multiplying everything by 1. So times 1 times 10 to the 9th over 1 times 10 to the 9th. So that gets rid of that and then leaves us with 1 meter is equal to 1 times 10 to the 9th nanometers, which is what we wrote there. So does that make sense? That people how to, we can read this base unit and then make our conversion factor. And so I would kind of use this, and why I handed it out to you is do this well, right? Make it your little cheat sheet so you have these conversion factors written. And then when you're doing the math, you just have to kind of glance over, okay, which one do I need? So let's do just a few more. So 1 times 10 to the 15 femtometers then is equal to 1 meter. course, we can flip that, again, depending on which way we're going. And so now let's look at some of the larger ones. And so again, this is times our base unit. And so now this is saying that, so 1, we'll stick with meters, so 1 terameter is equal to 1 times 10 to the 12th meters. So again, just multiplying now. And we can write it the other way. So 1 times 10 to the 12 meters is equal to 1 terameter. Skip over to mega. So 1 megameter. And notice mega has a big M. So not to be confused with our little m for milli. And not to be confused with our mu for micro. So it's that little funky like U thing with the tail. So that's micro. So mega, so 1 megameter is equal to 1 times 10 to the 6 meters. Since again, that's by our base unit. We can write that the opposite way, just flipping it around. Then I'll do kilo. So 1 times 10 to the 3rd meters is equal to 1 kilometer, or vice versa. So I'll let you fill in kind of the last stragglers on here. You kind of get the point. So now, let's set up how to do our dimensional analysis. And I probably wanted more space for this, but, oh, okay. I didn't know it would give me some space. So to set up our dimensional analysis, and so this is super important, and so we're going to go slow and explicit. So we want to start with what we're kind of starting with. So we just write that. So 5 meters. And sometimes I put it over 1, just so, again, I can kind of see things clearly. And then the next thing we want to do is we want to get our proper conversion factor. So what is going to get us from meters to kilometers? And then so looking at our final unit, so we want kilometers. And so that means for our conversion factor, I probably want something right with meters on bottom, so that will cancel out. Kilometers on top. And so we can look back if we need to at our conversion factor. And so which one of these would I pick? So the left one here or the right one? So excellent. I'm glad everyone was fast on that. So we have kilometers on top. So that's what we want. So this is the factor that we want to pick. So now we can add, so 1 kilometer is equal to 1,000 meters. And so now all we have to do is plug that in. So we can either practice our mental math, which is always good for you, or I'll plug in a calculator, again, just to be really explicit here. Oops, so 5 divided by 1,000, and so that gives us 0.005 kilometers. So let's do, I think class ends at like 6:20, and I'm trying to, oh, we have like 10 minutes. So let's do what I call these either trickier ones. I call them 2-step conversions. So if you're smart, you might just see it. So if you're looking, maybe I shouldn't say smart, but if you're, more inclined or you have more experience working with these, some of you may see the factor going from milli to kilo right away as being 1 times 10 to the 6. But I only know that because I've been teaching this course a bazillion times, and so I know what to expect. But how do we go from this? So I call this a 2-step because we're kind of going over the bridge here. So we have our base unit would be sitting right, somewhere here, our base unit, but we're going from milli past our base unit to something of a higher exponent. So what I would do is I would do this two-step conversion. And so let's start again with 60 milligrams. But then let's go to grams first, because that's something that we're probably comfortable with. We can look at our conversion chart, get to our base unit. So let's do conversion factor, and I'll put grams first. So we'll go to grams. So I want grams on top, milligrams on bottom. So 1 gram is how many milligrams?
1 gram is 1,000 milligrams.
So 1,000. Okay, so this is good. So milligrams cancel. So we don't have to solve anything yet. But now we can see, okay, we're at grams. Now what's our next conversion factor? So now we need to go grams to kilograms now. So kilograms on top, gram on bottom. So 1 kilogram is how many grams?
1,000.
So 1,000. So there now we can see more easily our 1 times 10 to the factor, 1 times 10 to the 6th factor of difference, or again, it's just easier to go step by step. And so now we can plug this in to our calculator. And I'm gonna skip slightly. So do y'all know how to add exponents, right? Like if you have 1 times 10 to the 3rd times 1 times 10 to the 3rd, you know that's 1 times 10 to the 6th, right? And that's just with, you can add those exponents. If I'm ever going too fast, just let me know, because everyone comes in at different math levels, so I just want to make sure everyone's on the same page. And so that gives me 6 times 10 to the negative 5th kilograms. Is that what other people got? So 6 times 10 to the negative 5th kilograms. And then I see a question in the chat. So the lecture will be live on Tuesday and Thursday. I'm hoping this YouTube thing will be smoother now that I've figured it out, maybe. Slash, I'll have to see what's up with my USB hub. But yeah, I'll do the same thing, streaming live at the same time. Let's do another one. So take a minute or two, see if you can do this one. So 77 meters to decimeters. So you can flip back.
So what the smallest and largest measurements will really be using in this class? I figured micro is probably a decent bet considering like microliters and such, but for like lab works and such, will we ever really have to work with the nano or pico or even femto units at all, or not really?
No, those generally don't come up in, at least not in like our normal lab setting, like a kind of the femto comes up if you're looking at like ultra fast lasers, for example. There was like a big
I was more
thing.
talking about for like homework problems or assignments or anything like that as well.
Yeah, I mean, I can't guarantee what's going to be on a homework assignment, but yeah, like regularly in lab, you're not going to see those crazy units. All right, so what did we get? So we have 77 meters. What's my conversion factor?
10
So 10 what?
decimeters.
So 10 decimeters are in 1 meter. So that cancels out. And then so what do we get for decimeters?
7.7.
Mm,
I'm just getting it to be the other direction.
yeah, so this is times the base unit. So what do we get for decimeters?
It's 770.
So 770, is that what other people got? Awesome. Let's see. So 770, I see it in the chat too. So the other thing I just want to emphasize in kind of our last few minutes of lecture is that, right, anytime you have a conversion factor, you can do this. So let's just say, so 1 inch is equal to 2.54 centimeters, right? So you can be given now, so that's your conversion factor. You can be given any conversion factor, right, of crazy units. And so now you know which way to go and know how to solve it. So we can convert 313 centimeters to inches. So we can do that, again, just using our dimensional analysis skills. So 313 centimeters. I know which way to write this since I want inches on top. So inches, 2.54 centimeters on bottom. And so now we can solve it. So 313 divided by 2.54. And so this would give us 123 inches. And so the other good thing about dimensional analysis and why it's really important is it helps you with like other multi-step problems. So you always want to make sure that your units make sense. So your units should all work out to the final units, like especially in physics, this is really useful. And so that's another trick. So I think we have to end here for today. So we'll pick up on Tuesday, so we'll finish off with the sig figs. If you need to take more time for your homework, that's fine. If you can't get it in, I'm pretty lenient with deadlines. So if you wanted to wait, that's fine. So we'll go over the rest of this on Tuesday and then continue on with the chapter. Yeah.
So, I know that on Blackboard it says that homework or like the assignments for week 1 are due on the 11th. Are you saying that we can still turn it in, but on Tuesday, which is I think the 12th?
Yeah. So I don't penalize for late work just because, we're still coming off of COVID and people have all sorts of schedules and conflicts. So I'm pretty lenient. The deadlines are more to keep us on pace, because if you don't stay on pace, right, you'll have 1,000 things due at the end of the course. So yeah, if you want to turn it in on Tuesday, that's perfectly fine. And then we will have lab next week, so that'll be exciting. And yes, it'll be live every week, so Tuesdays and Thursdays, lecture, from 5 to 6:20 or whatever, and post it on YouTube. I'll stick around on stream in case there are questions, but I'll handle in-person questions too. So that's that'll be in lab, so we'll do that next Tuesday. But yeah, you kind of have a head start on it. Yeah, but it'll probably make more sense if you do it all in lab. So recitation is more like a study hall. I would treat it as such. So I do like separate online recitations because I just can't get the individual attention. But you don't have to come or anything, I don't take attendance. It's just a good time to ask questions about like lab and homework
Oh,
if
okay.
you're struggling. Yeah,
Alright. I can make it some weeks and not others.
Yeah.
Because I work, so
yeah,
that's why I asked.
yeah, so it's not like super important that you be there.
Okay. Alright, well, thank you.
You guys can, if you have a question, you can ask first.
Oh, no, I didn't. I'll, see you next week.
All right, see ya.
Might
So-
I have a proposition to add as a homework problem?
No.
I'm not gonna change the homework.
I know you're not going to, but all I'm saying is, you should do use the furlong to help with the conversion unit specifically. It's 1/8 of a mile.
Don't you dare.
Maybe for an exam question.
Maybe. Anyway,
And yeah,
Even though
so
we're not really
both
gonna-
lectures will cover one chapter.
even though we're not really gonna be using those, I just wanted to add them for completion, then add the angstrom over there just in case. And then also, with plasma, would that fall closer to like a Bose-Einstein constant or those other special states as opposed to the standard 3? Or would it fall closer to like I said, the standard liquid gas solid?
I'm not really sure how it would compare to like Bose-Einstein constant versus like the
yeah.
other three, where,
As, like,
where they have
it's-
it classified.
As like a plasma is like the electrons are like essentially free flowing, if I'm remembering, or is that incorrect? Like it's more an electron soup kind of thing, right? Like the electrons have sort of separated, or
Yeah, I would have to look it up too as well to see
'cause I
like,
know Bose-Einstein constant is like where the molecules are able to sort of pass through each other as it's sort of achieved like it's a single quantum entity, which is really fun. Anyway, yeah, that mainly conversion. Anything else I have questions with? I'm doing the whole significant figures thing, right? As this would be like 5 since it could be between, and then you could round it specifically like that.
well, for the ruler, right, you want to estimate, so you have 5 point, so you know it's 5 something, but then this last digit you can guesstimate. So we don't know if it's like 1 or 2, but so that's what you want to guesstimate. So here we can guesstimate to the 10th. And then this one we know to the
Oh yeah, we can
100th.
guesstimate. So this is what we guesstimate specifically.
Yeah.
And I know with specifically multiplying significant figures, we only take. I'm not sure which page it's on. I'm sorry. Which page it's on? I think it's maybe at the back. Anyway, I know with significant figures specifically, you only take the least rightmost decimal place, like the.
Yeah,
Basically, the
if
one with
you're-
the fewest decimal
Yeah,
places.
if you're adding and subtracting, you just take the fewest after the decimal point. And then for multiplication, division, you have to determine like total number of sig figs. And then the smallest one dictates your answer, but that's
Yeah.
just for the total.
Yeah. And I'm guessing you convert sig fig, and you convert sig fig. Yeah, you convert sig figs at the very end of the process, right?
Yeah, so you
Okay.
don't want to do any rounding until the very end.
Process. So besides this, is there any other homework?
No, that's the only homework.
Okay. Have that set up.
You want pumpkin cookie or pork jerky?
All right, Ben, we can figure out something with the announcements, because I'm pretty free, like Monday, Wednesday, and Friday, where we could do a dedicated recitation. I just don't know what would work best with people's schedules. So if you tell me like what would work best for you, you know, I'm more than happy to kind of set that as a time. And then it would just be the, kind of the same thing that we do with the in-person. It's just, it'd be all online, and then we could kind of focus. It'd probably be on Zoom, so I could do like the whiteboard thing that's on Zoom with the screen share, so that students would be able to kind of write what they're doing as well. Otherwise, I just offer like office hours kind of at any time available for students, just by appointment.
Are you? I said glad the first class isn't really anything that complicated.
Yes, always.
So I'm still on stream for a little bit, just hanging out. I'll be here for probably another minute or so. Yeah, so basically recitation is just to clear up any questions. So again, I'm more than happy to do an individual appointment, yeah. Or sometimes what happens, if there's like a lab that's particularly difficult, I'll go over that specific problem in recitation. And if that is the case, I can always, record something as well. Any other questions or anything? I'm still hanging around on stream. It is not required to attend, it's just required to sign up for one. I know, it's kind of confusing. So you just have to be enrolled in recitation, but we don't do anything that's required. It's not really part of your grade or anything. It just has to be,
Signed up for?
yeah, exactly, you have to sign up for one.
So what you're saying is if I have to miss any class specifically, miss the recitation.
Exactly.
Got it. Not that I'm going to schedule things for it, but it ought to be a helpful buffer thing with stuff going on.
Yeah.
Last night, so nobody's super energetic, but last night I found him just on the beanbag chair.
Oh,
and poor
no.
thing, like I tried to get him to call out to him, and he tried to walk, but he just can't support his own weight. Like his nerves work, but like his muscles don't, so like he can't really move himself. Took him to the vet, but blood work and like X-ray were fairly inconclusive. He couldn't figure out what's wrong. If we wanted to figure out for sure what's really wrong, we'd have to get like an MRI, CT scan,
Oh,
and those
man.
are like $10,000 kind of thing. Have to
Oh.
drive all the way up to Springfield, you know?
That's crazy.
But we got some painkillers and muscle relaxants for him at least. And then when I was trying to come here, my mom asked me, like, after we picked up my car, like, oh, can you stop and get me garlic nuts? And I'm like, fine. Like, oh, I forgot you were class. I'm like, I don't know. I figured you'd remembered and it factored into some master plan you had. I'm sorry. A wonderful day.
All right, have a good one. All right, thanks everybody online. Thanks, Ben. Thanks everybody else too for your participation. Sorry that it was a rough start. Hopefully it will go more smoothly as I stream more. So thanks again. I'm going to end the stream and